And here you match the diffraction pattern with the crystal morphology, right? That along which axis the crystal is growing more and along which axis the crystal is growing less. So when you take, this is the orientation of the crystal, you didn't change the orientation of the crystal and took diffraction pattern from it. So if the diffraction spots along this direction are 100 and the crystal appears like this, then the longer dimension is 100. If this dimension is 010 in the diffraction pattern, then this dimension is 010 of the crystal. And from here you correlate the directions and the growth of the crystals using the diffraction pattern. You cannot say without the diffraction pattern that which direction or which lattice parameter is along that particular direction or along the other particular direction, right? Now, people don't rely on single techniques and they go for more and more accuracies and supporting techniques to confirm what they have found with the electron microscope, because the main deficiency of the transmission electron microscope is that it gives you information about a very limited area, and that limited area is just like you take a small stone from a mountain, right? You take a small stone from a huge mountain. So will that small stone represent the whole mountain? The answer is no. Small stone cannot represent a whole mountain. And in the microscope, you bring a stone, small stone from the mountain, then cut it into a small 2-3 centimeter piece, then grind it up to 100 micrometer thickness, then drill out a 3 millimeter diameter ring, then dimple it up to 25 micron thickness, then skip that surface with the argon ions to get a 20 nanometer thin area, and that 20 nanometer thin area will be also less than 1 millimeter. So the total volume of the sample you are studying is the thickness into area of that. So 1 millimeter into 1 millimeter is the area, for example, and thickness is 20 nanometer. So how much area is there? And you are deciding your science upon that small area. 1 into 1 millimeter is 1 millimeter square. The thickness is 20 nanometer. 20 into 10 power minus 9 multiplied by 1 into 10 power minus 3. 1 millimeter is minus 3. Minus 9 and minus 3, minus 12. So your total area is 10 power minus 12 meters square. How much is it? Very, very small. And you are deciding your whole mountain on the basis of that sample. So that is why the selection, the selectivity, the very minute fine selectivity of the electron microscope is its main drawback. And for that reason, whatever you get with the electron microscope, you check it with the scanning electron microscope. We check it with X-ray. We don't rely on one sample. Because if I am knowing about this brush, I will take one sample from here, one from here, and one from somewhere here. Then I will be a little bit able to say that the average results got from various areas of that particular mine give me this information. But which I told you that they appear lathe-like. These are the lathes of inertite. And that particular region which I showed you, which was showing in electron microscope, a very small lathe, actually that whole area was filled with these lathes. And that area, which was spheroidal crystals, it was that. So I took that, right? So when I did that scanning electron microscopy and I knew about the general morphology of these crystals, then I decided that okay, this is this particular material and it looks like that. And at the same time, I did XRD of these samples and found which phases are forming after different heat treatments. This is a different composition. I am showing just as an example that I did XRD after different hours of treatment at a specific temperature or a different temperature. So you do XRD of the sample, then you do scanning electron microscopy of the sample, then you go to the individual crystals in the transmission electron microscopy, then finally the beauty which you see that I say that this is this particular crystal and I want to know about that is by matching the latest image with the diffraction pattern, that are the atomic planes I locate are matching the all the corresponding diffraction spots are not. So from that I know about I compare what I see in the real space and the reciprocal space. So this opportunity is the plus point of the transmission electron microscope, right? So it takes you from the macroscopic world up to the nano and angstrom scale world of material. And it tells you about the huge nature of your universe. That when you go into a very 3 millimeter disk of a sample, it has a complete world of its own in it. And only transmission electron microscopy can take you there. So, transmission electron microscopy, chemistry, morphology, and crystal symmetry. All the three things are there. X-ray tells you about the crystal structure, but the minute details of the crystal structure, space groups, and all these things are sometimes not possible with X-ray, and you need transmission electron microscopy and very high resolving power devices to know about such things. Any question? Yes. Three D image, basically when you combine, I told you that if the crystal is lying like this and you move it, tilt it, you can tilt it up to here, right? It was like this. You tilt it up to here, you tilt it up to here. You can't tilt up to here. There was an old microscope which I used during the late 90s. It was 200 CX Joule microscope. It was very flexible in moving the sample. And I could do it. It could be turned in this direction 45 degree and in this direction 45 degree. It gives you two dimensions, right? Two dimensions are on the plane, and that can be taken as the third dimension if you could go up to 90 degree. But when you go to the fineness in the resolution, it limits your space. The higher the resolution, the more careful you are, your movement becomes limited. So nowadays, you cannot go beyond 30 degree tilt. 30 degree in this direction, 30 in this direction. So you can't go there. But when you are talking of anisotropic properties, then obviously you are taking images along different direction, because the microscope image, if you look into this, it is not a single crystal. One crystal may be with the 001 zone axis. The other may be with 100 zone axis. The other may be at 010 axis if it is a polycrystalline material. So you can take the images along different direction and you can combine them to make the holistic picture of the material. And the properties variation along different directions, if that anisotropy is present, if the properties are anisotropic, they are not uniform along all directions, then for that purpose, you usually rely on either polling the material so that the domains you need specific, they are aligned along a particular direction, or you use single crystal. Because when you make a large single crystal, then you can decide which phase or which direction is giving me the optimum property. So you utilize that specific direction and avoid the others. Okay? Thank you very much for listening.